All right, guys, it's time for Fun with Math, and today we're to do our final application of the method of increments. And so here I chose to apply this. We're basically going to do what's called density, mass, and work. So what we're going to do is we're going to use the method of increments to find first the mass of an object, and then next we'll use the method of increments to find the work. And so remember what work is. Work, this is a physical concept, and it's always equal to force times distance. This is actually pretty easy to kind of understand. It's like, here I have an object. How much work is it to move it from this point to this point? Well, I just take that object and I move it, and I get some work. And if you have a heavier object like this, and I move it from this point to that point, I do work too, but it should be a little bit more because it's more work to do this, to move this, than it is to move that, because this one has more mass, basically. And so the formula for that is basically you take the force that you have to kind of apply to that object, and then you multiply by the distance you move it, and you get this idea of work. And so we'll talk about this in a little bit, and we actually measure work in what are called joules, just if you want to know. And a joule, I don't know if you guys have had any physics, but force we usually measure in newtons, and then distance in meters. So a joule is a Newton meter, basically. And so what we'll do is we'll first do the mass of an object here in a minute. We're going to do it with rods, which is, just draw basically a horizontal line and imagine that's like a rod. And then something called lamina, right? So a lamina is basically a planar region. And you think of that planar region having some sort of density, basically, like a constant density, usually going across it. And that's what we mean by a lamina. And then for work, we'll wind up in this video, we'll do ropes / chains, because ropes and chains are basically the same thing. You treat them the same way when you do work in calculus. And then on the next video, we'll talk about it doing work with respect to tanks. And so we'll have like rectangular type tanks, circular tanks. We'll even have a triangular type of tank. All right, so let's just take a look at some of the problems here we're going to do. So the first problem, what do we want to do? We want to find the mass of a rod that is 10 meters long and has a density of delta of x. And so this is the Greek letter delta. And so it stands for the letter D, basically. So delta of x is equal to e to the negative 2x kilograms per meter. And the fact that's per meter is important because you can use the units. I call that the units trick to kind of figure out the mass. A dangerous trick that can get you almost through all physics without understanding what you're actually doing. But I'll show you that in a minute. Measure the distance x from the left end. All right, so let's draw our picture. And so for our picture, we just draw a rod. So I just usually draw a horizontal rod here. And then the idea from the left, this is going to be our distance x. And then what we're going to do is we're going to compute a small change in the mass. So I'm going to take a little piece right here as a little delta x. And my rod, I have to remember, is 10 meters long. And I can compute my little equation, my little increment, as a small change in the mass. And don't forget, my density function. My density function, delta of x, is equal to e to the negative 2x. So the idea with the picture, kilograms per meter, is to write down all the important information. And so for a small change in the mass, so we're basically looking, how do you compute a small change in the mass if you just take a little small change in x? Well, you just take your delta x, your density function, and notice it's per length per meter, and multiply by delta x. And so here the meters will cancel with the delta x, and I'll leave you with the kilograms. So there's a small change in my mass, which is actually equal to, we can plug in here, e to the negative 2x delta x. And so now what I'm going to do is I'm going to let the integral add up all those small little increments. So just add up each of them and let them go basically to an infinitely small piece, basically, when you take that limit. And so you're going to get the mass is equal to the integral. We start x from back here, so we're going to go from 0 to 10 meters. So 0 to 10. And then I have e to the negative 2x. And then my delta x, my little delta x becomes a dx there. And so I'm just adding up all the little pieces and the integral is going to tell me what that mass is. And so now I need to integrate this, so they can do this by guessing and checking. So it's e to the negative 2x. And then when you check it, the derivative of this thing is not quite that. When you take the derivative, you e to the negative 2x times the negative 2. So what I'm going to do here is I'm going to divide by negative 2, and then it goes from 0 to 10. And so now this thing is equal to, it's equal to what? So I have a negative 1/2, and I'm going to plug in a 10, so I get e to the negative 20 minus, and then I'm going to plug in 0, so e to the 0. And so that's going to be equal to negative 1/2, and then I have 1 over e to the 20 minus 1, which is really equal to, I'll put in that minus sign through, so 1/2, 1 minus 1 over e to the 20. And then don't forget the units. Now this is not length, it's not area, it's not volume, it's mass. And so it's just kilograms here. So little kilograms, so kilograms. And there's my answer. And so that's how you find the mass of a rod that has a density function. Right? So the idea is that this rod probably doesn't have uniform thickness, right? So well, I guess it could if it was different materials, but the density is not the same, so it weighs more in certain spots, kind of like a bat in a sense. Okay, what's next? Let's take a look. All right, so next we want to get into find the mass of a region. So we did sort of like a one-dimensional sort of figure. Now we're going to do a two-dimensional figure. So this is the mass of a lamina, which was, we did the mass of a rod. And so remember, the idea of a lamina, it's just like this kind of enclosed planar or bounded planar region that we imagine has a little bit of a thickness. So you have this sort of density function. It doesn't have to be constant. I think I said constant before. It doesn't have to be constant. So here you have a density function, but you kind of imagine it has a little thickness to it. Okay, so find the mass of the region in the figure below if it has a density of delta x equal to 1 minus x kilograms per meter squared. So here's my little picture. And so what I need to do is I want to find a small change in the mass. So to do this one, instead of taking like just a little piece, I'm going to take a little piece, but it's going to be a rectangle. So I'm going to find a small change in the mass of that thing. And so this is going to be my delta x right here, and this is going to be my height. And so my little equation, my little increment, my little delta m is going to be equal to h times delta x. And so what I need to do is I need to figure out h. So to figure out h, it's this height right here. I need to figure out the equation of this line, basically. And there are two ways to do this. I can be super clever about it and use my intuition, because I actually can write this down if you want me to. So this is y equals, the y-intercept is 2, so it's plus 2. And then the slope is what? Well, it has a rise of 2 and a run of 1. So it should be 2 over 1, so 2 times x plus 2. That's the formula for that line. That's just that using the idea of y equals mx plus b. So I can write it straight up. And if you've come, oh, I made a mistake. Don't forget the negative. It's going down, right? So you have to have a negative 2x plus 2. You could check it on your graphing calculator too, and you'd catch that negative. So I can use my intuition, but you saw my intuition can sometimes be faulty because I'm just using like what m and b are, and I have to remember that, when the slope is negative, when the slope goes down, it's negative. Or I could use formulas. So if I'm going to use a formula, I usually use this point slope form. So y minus y sub 1 equals m times x minus x sub 1. And I have a point right here. I'll just take this point right here. This is the point 0, 2. And so that means I have y minus 0 is equal to, then I'll use a space right here, and then x minus 2. And to figure out my slope, well, that's actually pretty easy. M is equal to delta y over delta x. Or if you want to use this formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So I'm just trying to compute the slope here. And I have a second point right here, which is 1, 0. So what I can do is take the difference in the y's, so 2 minus 0, and then divide by the difference in the x's, so 0 minus 1. So 0 minus 1, which is 2 over negative 1, which of course equals negative 2. And so I get negative 2 here. And so then what happens here is I get what? Oh, I think I put these in the wrong spot, guys. So I need to erase some stuff here. So let me erase. I put the 2 here in the wrong spot because this is the point 0, 2. So 2 goes here and 0 goes there. And so now what do I have? I wasn't going to get the right answer otherwise. Y minus 2 is equal to, I'll multiply through here by -2, so I just get -2x, add 2 to both sides, and I get y equals -2x, sorry, plus 2. So there's another way to find this. It's a little bit longer, but it also works. But you can also make mistakes in there too. So, as long as you show your work, you can get some good hefty partial credit. So why did I do that? Because I'm looking for the height, and the height is just my y value here, which is -2x plus 2. So it's actually -2x plus 2. And then that's all times my delta x. And so now I can integrate this. So m is going to equal, I'm going to add up all these little masses. And so I get the integral from, with respect to x, I'm going to go from 0 to 1 right here. So 0 to 1 of -2x plus 2. And then I have, I missed my density function, guys. So up here, notice I never use this guy here. So I have to actually have my density in here. And so there should be a great big delta of x right there. So let me move some stuff around here. I completely missed that. So here, you're gonna let me move this thing. You're gonna make me suffer. It looks like it's gonna make me suffer here. So let's just erase this. I'll write it back down. So what I had down was what? What I had down was just the area, right? So I just had delta A down. So I had delta A, which was what? H times delta x. But I didn't have that density function, so I actually wasn't computing the mass. I was computing the small change in the area. So I need to have delta x right here, and then times delta A, because then the units cancel, right? That's that unit trick. You see, how do you line up the units so you get the right thing out? You want kilograms out because that's mass. And so you got to multiply by a small change in the area. And so here I can plug in then this 1 minus x for the delta x. And then I know what my delta A is. It's h times delta x. And so that's going to equal to then 1 minus x, and then times this -2 x plus 2 delta x, which actually can be simplified a bit. So this -2, I can pull out a 2 basically, because you'll see here, this is 1 minus x, and I'll pull out a 2 here. I get -x plus 1 delta x, which actually equals 2 times 1 minus x quantity squared delta x, which is kind of nice. And so now when I integrate this to find the mass, so now I'm on the right track. So now when I integrate this to find the mass, I have 2 times 1 minus x quantity squared, and the deltas become a d, so dx. And so then this is going to be equal to, and now this one you can actually integrate by guessing and checking. So check it out. I would probably guess 2 times 1 minus x and then cubed divided by 3. This only works if you have a constant up there. And I'm going from 0 to 1. But then when I check it, I'm looking to see what the derivative of that guy is. So when you take a derivative, that 3 is going to pop down there, and you're going to get a 6, but the divide by 3 is going to give you back to 2. That's going to be squared. And then times the derivative of the inside, it's going to be a -1. So notice the idea is you'll have 2 times, the 3 will pop down, 1 minus x squared. It's still divided by 3, so the 3's are going to cancel, but then times a -1. I don't want that -1 there, so I'm going to pop a negative in front here, and that should take care of it. And so now this is going to be equal to a -2/3, and then I'm going to plug in my 1. And so when you plug in 1, you just get 1 minus 1, which is 0 cubed over 3. And then minus, I factor that -2/3 out, plug in 0, so I get 1 cubed, which is 1 over 3. And so that's going to equal a negative times a negative. That's going to be a positive 2 over, what is that? 9, right? So 2 9. Oh, gosh darn it. Let me tell you guys. I don't know why I put that 3 back there. I pulled that 3 out. All right, so I factored out this -2/3 right here. So when you plug in 1, you just get 0 cubed. When you plug in 0, you just get 1 cubed here. And so now I just get what? I get a negative times negative is a positive, and a 2/3. And then don't forget the units, kilograms. All right, so lots of good stuff on this little problem here. Lots of good mistakes, right? So pay attention. It's easy to make mistakes, and so show your work, and you get all that good partial credit. All right, we got one last problem that I want to do with you guys here. So I want to do a work problem. So, oh, let me fill this out. This is our solving part too. And if you want, oh, don't forget, you can test this. And remember how you test it? You just bust out a calculator and you can test that integral. And that's how I probably would have found a lot of my mistakes. You know, if I didn't catch them, I'd put it in a calculator and realize, ooh, I integrated, did something silly. Happens all the time. All right, so let's take a look at a work problem. And so remember, how do you find work? So the idea of work, and this is something we'll have to memorize for this class, if you want to find work, it's equal to the force times the distance. And so normally we just kind of abbreviate that W is equal to F times D. And the way we're going to find this is we're going to find a small change in the work. And then what we'll do is we'll add up all those works, and that'll give us our final answer. So let's take a look at the question we're going to do here. So we're going to do something with ropes and chains in this video, and we'll do the tank problems in the next video. And so what do we have? It says we have a 20-meter long rope with a uniform density of 2 grams per meter. It hangs over the edge of a building 50 meters tall. How much work is done by pulling the rope to the top of the building? All right, so let's draw a building here. So here's my picture. So here's my building. And I'm going to take a rope and hang it off the building here, basically. So I'm hanging a rope. It has a total of 20 meters. And I'm hanging it off the building. So I'm going to call this direction. I got to kind of put an X direction. So what's kind of neat about these problems is you kind of get to pick the arrangement of your coordinate system. So I'm going to just start my X up here and then go down here. So this is my X, basically. And then what I'm going to do is I'm going to take a small piece of this rope right here, a little delta X. I'm going to imagine I pull that little delta X piece all the way up. And I want to compute the I want to compute the work it takes to pull that little piece up. So over here on my equation, oh, and this is 50 meters tall. And I should write my density function down to here. So delta is equal to 2 kilometers per meter. All right, so I want to find a small change in let's use this orange color. So small change in the work. So I'm looking at how much work is to pull up that little piece. So the work, remember, is just this idea of force times distance. And so here for our force, what is it? It's really a small change in the force is what we're actually computing here. But the idea is I need to figure out this sort of mass times acceleration. You guys remember this from Newton's laws, F equals ma. And so for us, it's F equals mg because the acceleration is due to gravity. So here we have a small change in the mass. That's this little small change in the mass here. And then times our little g, and then times the distance. Now the distance is, we're going to move it through, is x. So we'll move it through x. And then what's the small change in the mass equal to? Well, that's where this density function is going to come into play. And so the density function, you notice you just multiply by a small change in the distance. So that's just that small delta x right there. And so I'm going to do what? Just my delta. Oh, maybe I'll write it out. So I'll do my little delta times my little delta x. And then I have my g times x, which is actually equal to, my delta is just the number 2. And I have my g, I'm going to do 2g, kind of rearrange the terms here, x, and then put the delta x at the very end. And now that's how much work it is to move a little teeny tiny piece, that x distance. Now I'm just going to take all those little pieces of work and add them up. So the work is equal to, and I'm going to integrate, and it's basically going to go from 0 to 20. That's the length of the rope, basically, right? So it goes all the way down to 20. And so I have the integral from 0 to 20. And then I have this 2gx, and the delta x becomes a dx. And now I can compute the amount of work just by simply integrating. So it's going to be equal to, and then this is basically, just do what? Gx squared from 0 to 20, which is equal to g times 20 squared minus 0 squared, which is equal to 20 squared is 400, so it's 400 g. And for g, we're always going to use the number 9.8, and that's meters per second squared. So that's the acceleration due to gravity. So here, now we can just approximate basically, if you want. So now this is approximately, well, we'll write equal since we're letting it equal, but it is an approximation to the gravity. So times 9.8. Whenever we get into these apply problems, the approximations and the equals are a little hairy. So we'll just write equals. And so I'll need a calculator for this. So if you have a calculator, I don't have mine on my screen right now. I can crunch it. So 400 times 9.8, and I get out what? 400 times 9.8, and I get out 3,920. 1,920, and that's Newton meters, but those are actually called joules, basically. So joules. So 3,920 joules is the work it takes to pull this rope, which is 20 meters long, to the top of the building. Now notice we never actually needed the 50 meters. Where the 50 meters came into play is the fact that the rope is hanging off of the building and not actually hitting the ground. We never actually needed it in this problem. All right, so that's actually part one to this problem. There's actually a second part, and the second part says what? The second part here says now what would happen? Let me move this over a little bit. What would happen if we attached a bucket? So what would happen? How much work is done basically if we add 100 kilogram mass to the end of the rope? So the idea is you kind of add a little bucket here, and it has 100 kilograms. And so how do we find the work? And so at first it seems like it might be kind of tricky, but it actually turns out to be pretty easy. So to find the total work done, it's going to equal the work to pull the rope up plus the rope for the bucket. So I'll just use, actually, we can actually write these out. So bucket and rope and total, if you like. And so what's that equal to? Well, we just found the work for the rope. It was 3,920 joules plus, and then the work for the bucket, well, you just take the force times the distance. And so remember what the force is. So 3,920. The force is just the mass, which is 100 kilograms, times the acceleration due to gravity, so g, so there's the force, and then times the distance, well, you moved it 20 meters, so times 20. And so this will equal 3,920 plus, and you have 100 times 9.8 times 20, and then you get your answer. And so, again, just use your calculator to crunch it. And so 3,920 plus 100 times 9.8 plus 20, oh, not plus 20, guys, times 20. And out pops our answer. So 23,520, and again, these are joules, so joules. All right. So that's all I have for us today. See you later.